Hello everyone, and welcome to today's chem lesson. Today we are going to introduce our new unit, the atom, and what's inside it, by, excuse me, by walking through a brief history lesson. We're going to look at the model of the atom and how it developed over time. We're going to look at the ancient Greeks, which you see on the page in front of us here, and their theory on the atom, and how different experiments and accidents led to us getting the full picture of what an atom looks like. Now, the ancient Greeks were the first to think about the atom and put it into words. The fact that if you take something and break it in half over and over and over and over and over again, you will eventually get to a piece that is so small that you cannot break it in half again. And they named that an atom. They didn't have any idea of what it looked like, so they said it was a small, dense sphere, right? The smallest, densest sphere you could get. Right. This was their picture of the atom. And that idea stuck for a long time, right? It's ancient. And no one really had the tools or equipment to be able to really test anything else. And so this idea, this theory of the atom, this introductory idea of an atom, existed for a few thousand years. And then, in the late 1800s, people began experimenting, and we got little experiments here and there that led to one man, Dalton, taking all of those ideas and combining them together to make the atomic theory. Now, the atomic theory doesn't actually change the picture of the atom, but it does set a bunch of ground rules for how the atoms are going to behave, or what atoms should do and what they shouldn't do. So while this sphere doesn't change over time, we get a bunch of rules taken from a bunch of different experiments. All matter is composed of atoms. Atoms of the same element are the same. Atoms of different elements are different. Right? So if I have two gold atoms, they should be the same. And if I have a gold and try to compare that to an oxygen, it should be different. Atoms can't be subdivided, created, or destroyed, right? They're the smallest things you can get. Right? They cannot be destroyed. You can't break them down any further. You can't make them. And they're not made of anything else. Atoms of different elements combine in whole number ratios, right? That's the important thing, whole number. You never have C.60 1.2, right? It's always C102 H2O. There's never a decimal or a fraction when we look at formulas for compounds. They combine in whole number ratios. Because again, you can't have 0.6 of a carbon atom. That's not a thing. You can't have 1.2 oxygen atoms. That's not a thing. And lastly, is that in chemical reactions, atoms are combined, separated, or rearranged, which means that if I have something like this, if I burn methane, I end up with rearranging my pieces like Legos, right? Taking apart what I had to begin with and putting them together in some new setup. And while each of these things is great, they're not all true. Right? A lot of them are. A lot of them were discovered and found to be true, right? Whole number ratios is true. Combining, separating, rearranging is true. All matter is made of atoms is true. But we know that atoms can be subdivided, right? They're made of protons, neutrons, and electrons. We know that atoms can be created in the lab because we've done it before. We know that atoms can be destroyed with nuclear reactions. So we've done that before too. So we know that this third point isn't true. But in the late 1800s, nobody knew that. Nobody had discovered protons, neutrons, or electrons. Nobody had made atoms in a lab. Nobody had done a nuclear reaction then. And two, the second rule here is almost true. We're going to talk about isotopes. And they're the thing that kind of make this untrue. We'll talk about those in a later video. But it's really close to being true. The atomic theory is very close to what we know to be true today. And really, the thing that brought us to the model of the atom we use today is experiments trying to look at an atom, or trying to discover more about an atom. And the first person to make a discovery to advance us along in this story is actually a guy who did it by accident. J.J. Thomson was the first one to discover something new about the atom, right? He was operating under the assumption an atom is a hard, dense sphere, right? A small, hard, dense sphere. And he did some experiments with a cathode ray tube. What a cathode ray tube is essentially what a neon sign used to be made out of. I'm going to pretend I know how to draw and try that one again. Straight lines, please. Close enough. Close enough. Neon signs used to be made of these cathode ray tubes, and essentially when you run a current through them, the gas inside gets excited and glows a different color. We're going to use light blue in this example. And you get a beam of light, and if you shape the glass a certain way and shade the glass a certain way, you end up getting the signs that you're used to, right? Those like puffed up glass bubble signs. And what Thomson discovered is that when he brought a magnet near the cathode ray tube, it bent the beam of light. Instead of going straight across, now the beam of light was bent towards this magnet. And he looks at this whole situation and he goes, huh, that's weird. That's not what I was expecting to happen. And so he theorizes now that an atom is more than just a sphere. He says that there's stuff inside an atom. Stuff inside an atom that gets activated by electricity. Things that are negatively charged, right? Because they're attracted to this positive end of the magnet. Things that are negatively charged that get activated by electricity. And he called them electrons. Right, he says, okay, when I run electricity through these atoms, there's a negative part that gets activated. So an atom is not just a dense sphere, it is a positive sphere with little negative bits inside it. And because of this model, right, because of the way this model came about, he called it the plum pudding model, where there's a positive pudding with little negative electron plums. And that's the first step we have into the model of the atom that we know today. Was this accidental discovery of electrons. The next step was made by someone who was trying to prove that Thomson was correct. Rutherford comes along and he sees Thomson's model of the atom, he sees all of his papers and his experiments, and he says, okay, I want to help prove that this is correct. And so he sets up an experiment. he sets up an experiment that takes a small lead box that shoots alpha particles, teeny tiny particles, at a piece of gold foil. And he lines the whole thing with photo paper. And he says, this photo paper is going to develop any alpha particles that bounce away from this gold foil. And so he's looking at this, and his experiment says, I'm going to take ping pong balls and fire them directly at a brick wall. Right, I'm going to take these teeny tiny alpha particles and fire them at my gold foil. And what he expects to happen here is that all of the alpha particles will bounce back, and they'll develop over here on the outskirts, because they're going to bounce off of this solid substance, right? This dense set of atoms. But instead, what he sees is most of the particles travel straight through the gold foil, with a couple of them, right, a small percentage of them, bouncing back to develop on the outskirts. And he looks at this with confusion, and he says, I just fired ping pong balls at a brick wall, and they passed straight through. That's not right. Right? It should not happen this way. So I guess I don't have a dense sphere here, right? I guess atoms aren't a dense sphere. Sorry, Thomson, but I proved you wrong. And he says that an atom is mostly empty space, and that there is a small, dense nucleus within that atom, right? Not that the whole thing is a dense substance, but instead that there is a small, dense nucleus and a lot of empty space. But he didn't know how electrons fit into this. Right? He doesn't know where anything is. He just advanced the shape. Right? There's a small, dense nucleus. There's a bunch of empty space. And it really took the next scientist to really figure out where things were in the atom and develop the model of the atom that we are going to use in class. And that was Niels Bohr, who was an important scientist for a number of reasons, but the one that we're going to focus on is his model of the atom. Right, Bohr's model of the atom, Bohr's experiment, led to the idea of the shell model of the atom, where there are specific distances from the nucleus where electrons can exist. Kind of like planets circling the sun, there are these specific orbits that electrons can follow, these specific paths that electrons can follow. And his experiment involved a lot of energy being added to atoms and then measuring what happened afterwards. He specifically focused on hydrogen, right? And a lot of his experiments were focusing on hydrogen gas. And he found that when he put energy in, he always got the same couple of results back. And so what he said was that in the classroom of the atom, electrons fit only at desks. right? So an electron can come and sit at one of the desks, first row, second row, third row, doesn't matter. But they can't sit in between in the rows in the walk space. They can't sit on the floor by the window. They can't sit on the floor in the back of the classroom. They can't stand up and lean against the wall. Right? Electrons are limited to sitting at these quote-unquote desks, to sitting in these shells at these distances from the atom. They can't sit anywhere else. They don't fit anywhere else. They must go into one of the chairs, one of the shells, one of the desks. And this atom is what we're going to be using in class. We're going to be using the shell model and looking at how it works and what it does and what we can learn from it. But it is not the most advanced model of the atom. It's actually not the model of the atom that we use in modern science. The model of the atom that we use in modern science is the quantum mechanical model. The quantum mechanical model takes Bohr's idea and really refines it. It takes Bohr's idea that there are these distances from the nucleus that electrons can exist at, and it refines it down to something more complicated but much more accurate. It introduces the idea of orbitals, which are regions of probable electron location. Now let's keep our classroom analogy, right? Electrons are like students in the classroom. They're sitting at desks, and that's what Bohr said. The quantum mechanical model says if one of these students dropped a book on the floor and the dean is trying to find them to return the book, or somebody else is trying to find them to return the book, you know the schedule, right? You know this person's schedule. You know in what room they're supposed to be in, but you don't know what seat they're in. You don't know exactly where they sit in this classroom. You don't know if, when you arrive, if they've gone to the bathroom, or if they've made a trip to their locker, or if they're going for a glass of water. All you know is where they're supposed to be in third period, or in fifth period, or in sixth period. And so you don't actually know exactly where that electron is. You don't know exactly where that person is. You know where they should be. You know where they are most likely going to be. But you don't know exactly where they are. And the quantum mechanical model is the one that we'll use if you go on to AP Chem or take college chem classes. But for high school chem, for Regents level chem, we're going to be looking at the shell model as our model of the atom that we're going to use in class. And it's really not that different. There's going to be a couple of things that when we get to them, when we start talking about them, you'll see things that don't match up because the shell model isn't perfect, right? The shell model isn't correct. We know that there's a more advanced model out there. But for everything else we're going to learn, the shell model is a perfect level of difficulty. It's the perfect level of conceptualizing for us to get where we need to go, for us to learn the things that we need to learn without overcomplicating them. So it's important to know that the quantum mechanical model exists. It's important to know that the shell model that we'll be using is not 100% accurate, but we are still going to be using it because, just like we talk about ideal gases instead of real gases, it's going to make our lives easier, and it's not that big of a jump to go from shell model to quantum mechanical. And with that, I'm actually going to transition us over to our Zoom meeting for questions, comments, concerns, and attendance. And I will see you there.